Hi, good afternoon. My name is Yanzhi. I'm from UCSB, and today I'm going to talk about our work, visualization question answering using introspective program synthesis. This is joint work with Xifeng Yan and Yufeng. And this work is mainly about how program synthesis techniques can help explain predictions of deep learning models and further refine those predictions. And we practice this technique on a new domain called visualization question answering and show its effectiveness. And so here comes a bit background. So nowadays, deep learning models play an important role in many application tasks, as they also show effectiveness in practice. And the deep architectures consume huge amounts of data, which could also bring both benefits and troubles. And on one hand, if they work well, everyone is happy. And on the other hand, there are also concerns about the unpredictable behaviors of those models, in the sense that developers sometimes also have no idea of what went wrong when a deep learning model started to misbehave and predict the wrong answer. And especially when the size of a deep learning model has grown from around 60 millions to 170.5 billions over the last decade. And deep learning models are also applied to the task that we just mentioned, the visualization question answering task. So we use VQA for short here. So the VQA task consists of a visualization, as shown here on the right-hand side, and a query written in natural language from the user, as you can see here. And the goal is to find out the answer to the query via transformations to the visualization. And there is a broad spectrum of operations that you can do, such as projection, extraction, and arithmetic operations, such as aggregation or other like filtrations. And then, for example, here is a VQA task. On the right-hand side, there is a stacked bar chart showing different people's opinion on the economy of different countries. And on the left-hand side, there is a query written in natural language asking about which country's economy will get the worst in people's opinion. And then as a human being, we can stare at the visualization and then immediately figure out that, the country with the shortest blue bar is probably the answer that we want. Now the problem becomes like how we can actually design an algorithm to automatically figure out the desired answer that we want, right? And some prevailing approaches for solving the VQA task are mainly based on statistical machine learning. So there are two categories that I would like to mention here. The first one is the fully supervised machine learning methods, which, for example, include SymBob and NL2Code. And then these kind of methods, they still need a high quality of manually annotated logical forms or programs that can explain the transformation from the question to the answer. So usually what we have is that we have an input. The input is the visualization and the query, and the output will be the answer. And then this kind of model, it requires the manual user to generate the intermediate program, in which that when you execute this program, you can get the answer. So they need this kind of supervision, which is very expensive and very hard to get because you probably need an expert to get that. And then and there's a second kind of machine learning methods, which is called weakly supervised methods. So such kind of methods, the example one here is the Tapers model. And this kind of models, it does not require the manual labeled data, but the data collection will be cheap, but it's also noisy because you collect data from everywhere, and then there is no quality control, which may also create troubles to the result. And then based on observations and experience working on those mainstream weakly supervised approaches, because they only output the final answers to the VQA task. So they are kind of first of all, non-trivial for human beings to understand what's going on there. And the second, it is also very hard to fix any problems or mistakes when the model's reasoning is has something wrong there. And the question that we are asking here is that whether we can actually explain the predictions of the model so that we can perform further refinements to help human beings understand the model and further get the wrongly predicted answers correct. So that's our motivation. For example, on the right-hand side, I show you another very simple VQA task together with this one. This is a list of candidate answers provided by the deep learning model. And the user wants to know which country has the highest value and sort of things. And then the model predicts 4 countries, Brazil, Japan, China, and the US. And we only observe the final outputs. There is not much information that we can learn, except that all the 4 answers, they are totally completely different. But on the right-hand side, I also show you some two more examples that can be executing on the visualization to get answers. So here are diamonds. There are holes that yet to be determined. So these programs, they are partial program yet to be completed. And by executing the first program, we may get Brazil or Japan as the result. And then by executing the second program, we may get 4 countries, all of the 4 countries as a result, depending on the final choice of the aggregation operators that we're going to fill in those holes. So with the help of such background explanation program, we can actually reveal some more hidden arithmetic operation, semantic information that may help us further refine the model's prediction. How do we do that? So here, for example, I will show you here, because the user is asking for the highest improved value, and then those answers that can be generated by the background explanation program that has the max language construct or the production rule seem more promising, because the highest is very semantically similar to max. So in this case, Brazil and Japan are more likely to be the correct answers rather than the other ones, because their explanation has respected the user intention in their natural language query. So the question here becomes, let me rephrase the question a bit. Can we use the program synthesis techniques to actually dig out more background explanation programs based on the model's predictions? And this is actually a slightly different problem setting than the existing programming by example settings, because first of all, not all the predictions of the models are correct. This means we cannot rely on the top predictions of the model, but need to consider all its potential noisy predictions as examples. And sometimes the model may even generate completely wrong predictions. And the second is predictions may conflict with each other. This means we may need to choose different background explanations and find the best fitting one according to the problem, which is the visualization and the user query, right? So you may also wonder how well does a Strawman proposal would work, like a naive basic solution. Recall that the problem is to find explanations, programs that fits one of the model predictions and match the user query. So the most straightforward way would be, first of all, we invoke an off-the-shelf synthesizer to solve feasible programs using the visualization as input and using the model prediction, each of the model prediction as output. So we'll probably invoke multiple, synthesizer multiple times. And then next step, would end up with a bunch of different programs. And we may probably ask the user to actually tell you which one is the best, because we don't have a definition of consistency between the visualization and your query. So after thinking about this for a while, we immediately find some issues. So there are 3 that I list out here. First, a model may emit a large number of predictions. So in that case, synthesizing programs, we need to synthesize programs for each prediction. That will not scale well. And a more important one is that, second, the correctness of the final result heavily depends on the model prediction. So if none of the model prediction is correct, then all the synthesis done before will be meaningless and be wasted, because we're synthesizing we're not synthesizing any of the correct answers. And third, we don't have a formal definition of best fitting programs. We need some measurement to connect the 3 parties. So here, 3 parties means the first one is the different kinds of elements in the visualization. The second is the user intent, which is the query. And the third one will be all the candidate programs that you synthesize. And these 3 parties, that we need to maintain some consistency in order to respect the user intent and increase our chance to find the correct answer. So in this way, the Strawman proposal may not work out of the box. So that's the reason why we have the framework called POE to tackle with the aforementioned problems. So here's an overview. So given a VQA specification and an off-the-shelf deep learning model, the goal is to refine the deep learning model's default prediction by synthesizing explanation programs for them and pick the one that is most promising. And POE outputs the best answer it picks along with the synthesized program as the explanation. So the whole algorithm is 2-staged, namely abstract synthesis module and the optimal synthesis module. So the abstract synthesis module provides a scalable choice to synthesize partial but feasible programs for deep learning models prediction, so that the algorithm no longer needs to enumerate every concrete program and then finish all the synthesis code until the end. But instead, we use a top-down enumeration, and it could stop halfway and to only provide the partial program and handle the remaining part of the concrete program filling into the next module. So this will make things much scalable. And the next module is called optimal synthesis module. So in this module, we define the consistency metrics between the elements in visualization language units in query and production rules in the explanation program and encodes them into concrete programs as max SMT problem, which can be handled by solvers. So in the rest of this talk, I'll use explanation and programs interchangeably. So here's a brief walkthrough of our framework on the motivating example. So recall that the user query is to find out which country will get the worst economy over the next 12 months. So Paul first passes the visualization into its equivalent table format and provide it to the deep learning model. In this case, we use Tapas. And then next, the deep learning model gives a set of candidate answers, including Brazil, China, Japan, Greece, and so on. Based on these candidate answers, the abstract synthesis procedure will analyze and provide a set of candidate explanations like this. And after that, the optimal program synthesis finds out the optimal concrete explanation by invoking the max XMT procedure on the problem consistency encoding, which I'll discuss later. Okay, so for example, you can see here, there were two candidate concrete explanations here, explanation number 1 and number 2. And both explanations have the terminal called country, which aligns with the natural language unit in the query and also a cell value in the visualization. But for explanation 1, the key terminal in proof it actually doesn't match any of the elements in the query. But you can see that in explanation 2, the key terminal worsen is actually mapping to both some units in the query and in the original visualization. So in this case, the optimal synthesis module will consider explanation number 2 a more promising and optimal explanation and pick it and execute it to actually get the correct answer of this question. So the explanation actually considers the consistency in those like 3 parties. We call this triangle alignment, and it turns out that satisfying such alignment is actually, in addition to syntactic correctness, is actually a very strong hint to find out the true explanation. We'll discuss how to formalize this. And by the way, we actually have like a tiny toy DSL here for the talk, and then you don't actually have to memorize that because I will explain when necessary. Yeah, just to let you know there's something here. Okay, so there's a summary. So first of all, this is a summary of how like Poe's workflow looks like. It's very straightforward. First of all, we have a deep learning model outputs a set of candidate answers, and then we invoke the abstract synthesis module to narrow down a smaller search space of potential explanations. And then we have the optimal synthesis module to concretize the explanations and picks the best fitting one according to the consistency constraints. And eventually we get the refined optimal answer together with its corresponding explanation programs. Okay. And then we will slightly dig a bit into the abstract synthesis module. So we have a brief illustration of how this model affects the granularity and scalability of a search. So a dotted circle here that you can see is a program, and it could be, of course, partial. And a triangle here is an input-output example. And a triangle falling into a circle means that the corresponding program is actually feasible on the our examples. So our previously discussed strawman solution falls into the right-hand side, which is not super scalable because you need to perform synthesis for each input-output example. And then on the left-hand side, we directly synthesize the most abstract program, which is feasible to all IO examples. But in this case, we are delegating all the search to optimal synthesis, which is also less scalable. So ideally, our algorithm would like to provide a backup programs that are in the middle, neither too specific nor too abstract. So at this level, it should provide sufficient information about the program structure and then fit for the optimal synthesis module. So on the right-hand side, if we put in ourselves in the context of solving, it would be like this. The abstract synthesis will just first of all start from a hole and then gradually expand every production row, every hole, until it finds out that, oh, it's feasible for a designated number of answers, and then it falls back to actually pick one of the programs and then put it into the back and then fit it into the next module. Okay, and after that, the optimal program synthesis module is invoked. So as I mentioned, the intuition behind is to maximize the consistency. And then you can see from the right-hand side, the module had to consider the best way to fill in those holes from a partial program provided by the previous module. And there are two sets of constraints that we are implying here. The first one is the hard constraints, which is straightforward, which it will just like ensure that the synthesized program, they are like syntactically correct. And for the next one, which is the soft constraints, we focus on checking the similarity of the units in different parties. In particular, we borrow the notion of a near synonym in the linguistics community. So, for example, a linguistic engine that is capable of measuring such kind of similarity would attribute higher score between this high and highest, rather than high and low. So therefore, we can actually define our objective of soft constraints like this. The first part on the left-hand side is to increase the consistency matching between the candidate explanations, the visualizations, and the query. And the second part on the right-hand side actually adjusts the preference of explanations towards the more common ones. So this PPL that you can see here measures an explanation's perplexity, where the smaller, the less uncommon, that's more preferable. And then this makes sure that the module would not try to those like too rare explanation at the beginning. Okay, that's it for the technical part, and we will go to the explanation, the experiment. Oh, okay, so in the evaluation, we're curious about the four research perspectives of the tool: the performance, the effectiveness, explainability, and the application study. And we used 629 benchmarks proposed by VizQA, which is also the first and only benchmarks for VQA tasks so far. So POE is built upon TAPAS, which means that it can fix the TAPAS deep learning model's solution. And then as we can see, this direct comparison against TAPAS show that POE can get 23% more benchmarks solved. And then if we increase the chance a bit, it could get 27%. And a further comparison also showed that for different question types, our tool also apply quite well. So for more information and more different kinds of application study and user study, you can go to our paper for more details. Okay. So I think that's as a conclusion. So we propose POE, a tool that can help developers and even end users to understand deep learning models' predictions on visualization, question answering tasks. And we can also the tool can also fix potentially wrong predictions using program synthesis techniques. So our tool is also open source on GitHub. Feel free to have a try. And that's all I have for this talk. Thanks for your attention. With all this, I'm happy to take questions. Yeah.
Just have a quick question. So I noticed that some of the terms were highlighted. Are those like given by the user? Do you have a technique that automatically determines those and then will use those? Can you go?
Oh, so in the program setting, the user only has to provide the query. So the query in natural language is the only specification the user needs to provide. And for all those alignment, they are performed automatically by the tool. Yeah.
So the important words are determined automatically by your approach, by something that you have. Because you had some keywords that were like important in some sense?
Yeah, those are automatically extracted by the linguistic engine. Right.
Okay, so if there's further questions, you can have them offline afterwards.
Yeah, we can have them
and let's thank again the speaker.